Best response dynamics and the Nash Equilibria. Thus far, we have been considering local search as a technique for solving optimization problems with a single objective. In other words, applying local operations to a candidate solution so as to minimize its total cost. There are many settings, however, where a potentially large number of agents, each with its own goals and objectives, collectively interact so as to produce a solution to some problem. The solution that is produced under these circumstances often reflects the tug of war that led to it, with each agent trying to pull the solution in a direction that is favorable to it. We will see that these interactions can be viewed as a kind of local search procedure. Analogies of local minima have a natural meaning as well, but having multiple agents and multiple objectives introduces new challenges. The field of game theory proves a natural framework in which to talk about what happens in such situations when a collection of agents interacts strategically, in other words, with every trying to optimize an individual objective function. To illustrate these issues, we consider a concrete application motivated by the problem of routing in networks. Along the way, we will introduce some notions that occupy central positions in the area of game theory more generally. The problem. In a network like the Internet, one frequently encounters situations in which a number of nodes all want to establish a connection to a single source node S. For example, the source S may be generating some kind of data stream that all the given nodes want to receive, as in a style of a one-to-many network communication known as a multicast. We will model this situation by representing the underlying network as a directed graph G equals to V with a cost C which is greater than or equals to 0 on each edge. There is a designated source node S in V and a collection of K agents located at different terminal nodes T1, T2, T3 until Tk, which is in V. For simplicity, we will not make a distinction between the agents and the nodes at which they reside. In other words, we will think of the agents as being T1, T2, T3 until Tk. Each agent Tj wants to construct a path Pj from S to Tj using as little total cost as possible. Now, if there were no interaction among the agents, this would consist of k separate shortest path problems. Each agent Tj would find an S-Tj path for which the total cost of all edges is minimized, and use this as its path Pj. What makes this problem interesting is the prospect of agents being able to share the costs of the edges. Suppose that after all the agents have chosen their paths, agent Tj only needs to pay its fair share of the cost of each HE on its path. That is, rather than paying CE for each E on Pi, it pays CE divided by the number of agents whose paths contain E. In this way, there is an incentive for the agents to choose paths that overlap, since they can then benefit by splitting the costs of agents. This sharing model is appropriate for settings in which the presence of multiple agents on an edge does not significantly degrade the quality of transmission due to congestion or increased latency. If latency effects do come into play, then there is a countervailing penalty for sharing. This too leads to interesting algorithmic questions, but we will stick to our current focus for now, in which sharing comes with benefits only. Best response dynamics and Nash Equilibria definitions and examples to see how the option of sharing affects the behavior of the agents. Let's begin by considering the pair of very simple examples in Figure 12.8. In example A, each of the two agents has two options for constructing a path. The middle route through V and the outer route using a single edge. Suppose that each agent starts out with an initial path but is continuously evaluating the current situation to decide whether it's possible to switch to a better path. In example A, suppose the two agents start out using their outer paths. Then T1 sees no advantage in switching paths since 4 is less than 5 plus 1, but T2 does since 8 is greater than 5 plus 1. And so T2 updates its path by moving to the middle. Once this happens, things have changed from the perspective of T1. There is suddenly an advantage for T1 to switching as well, since now it gets to share the cost of the middle path, and hence its cost to use the middle path becomes 2.5 plus 1, which is less than 4. Thus, it will switch to the middle path. Once we are in a situation where both sides are using the middle path, neither has an incentive to switch, and so this is a stable solution. Let's discuss two definitions from the area of game theory that capture what's going on in this simple example. While we will continue to focus on our particular multicast routing problem, these definitions are relevant to any setting in which multiple agents, each with an individual objective, interact to produce a collective solution. As such, we will phrase the definitions in these general terms. First of all, in the example, each agent was continuously prepared to improve its solution in response to changes made by the other agents. We will refer to this process as best response dynamics. In other words, we are interested in the dynamic behavior of a process in which each agent updates based on its best response to the current situation. Second, we are particularly interested in stable solutions, where the best response of each agent is to stay put. We will refer to such a solution from which no agent has an incentive to deviate as a Nash Equilibria. This is named after the mathematician John Nash, who won the Nobel Prize in Economics for his pioneering work on this concept. Hence, in example A, the solution in which both agents use the middle path is a Nash Equilibria. Note that the Nash Equilibria are precisely the solutions at which best response dynamics terminate. The example in Figure 12.8b illustrates the possibility of multiple Nash equilibria. In this example, there are k agents that all reside at a common node T, that is T1 equals to T2 equals to T3 and so on equals to Tk, which is equals to, suppose it's equals to T. And there are two parallel edges from S to T with different costs. The solution in which all agents using the left-hand edge is a Nash equilibrium in which all agents pay 1 plus epsilon, then divided by k. The solution in which all agents use the right-hand edge is also a Nash equilibrium, though here the agents each pay k divided by k, which is equals to 1. The fact that this later solution is a Nash equilibrium exposes an important point about best response dynamics. If the agents could somehow synchronously agree to move from the right-hand edge to the left-hand one, they'll be all better off. But under best response dynamics, each agent is only evaluating the consequences of a unilateral move by itself. In effect, an agent isn't able to make any assumptions about future actions of other agents. In an internet setting, it may not even know anything about these other agents or their current solutions, and so it is only willing to perform updates that lead to an immediate improvement for itself. To quantify the sense in which one of the Nash equilibria in Figure 12.8b is better than the other, it is useful to introduce one further definition. We say that a solution is a social optimum if it minimizes the total cost to all agents. We can think of such a solution as the one that would be imposed by a benevolent central authority that viewed all agents as equally important and hence evaluated the quality of a solution by summing the costs they incurred. Note that in both A and B, there is a social optimum that is also a Nash equilibrium, although in B there is also a second Nash equilibrium whose cost is much greater. The relationship to local search. Around here, the connections to local search start to come into focus. A set of agents following best response dynamics are engaged in some kind of a gradient descent process, exploring the landscape of possible solutions as they try to minimize their individual costs. The Nash equilibria are natural analogies of local minima. In this process, solutions from which no improving move is possible. And the local nature of the search is clear as well, since agents are only updating their solutions when it leads to an immediate improvement. Having said all this, it's important to think a bit further and notice that the crucial ways in which this differs from standard local search. In the beginning of this chapter, it was easy to argue that the gradient descent algorithm for a combinatorial problem must terminate at a local minima. Each update decreased the cost of the solution, and since there were only finitely many possible solutions, the sequence of updates could not go on forever. In other words, the cost function itself provided the progress measure we needed to establish termination. In best response dynamics, on the other hand, each agent has its own personal objective function to minimize, and so it's not clear what overall progress is being made when, for example, agent Ti decides to update its path from S. There's a progress for Ti, of course, since its cost goes down, but this may be offset by an even larger increase in the cost to some other agent. Consider, for example, the network in figure 12.9. If both agents start on the middle path, then T1 will in fact have an incentive to move to the outer path. Its cost drops from 3.5 to 3, but in the process the cost of T2 increases from 3.5 to 6. Once this happens, T2 will also move to its outer path, and this solution with both nodes on the outer path is the unique Nash equilibrium. There are examples, in fact, where the cost increasing effects of best response dynamics can be much worse than this. Consider the situation in figure 12.10, where we have k agents that each have the option to take a common outer path of cost 1 plus epsilon for some small number epsilon greater than 0, or to take their own alternate path. The alternate path for Tj has cost 1 over j. Now suppose we start with a solution in which all agents are sharing the outer path. Each agent pays 1 plus epsilon divided by k, and this is the solution that minimizes the total cost to all agents. But running best response dynamics, starting from this solution causes things to unwind rapidly. First, Tk switches to its alternate path, since 1 divided by k is less than 1 plus epsilon divided by k. As a result of this, there are now only k minus 1 agents sharing the outer path, and so k minus 1 switches to its alternate path, since 1 divided by k minus 1 is less than 1 plus epsilon divided by k minus 1. After this, tk minus 2 switches, then tk minus 3, and so forth, until all k agents are using the alternate paths directly from S. things come into a halt here due to the following fact. 12.13. The solution in figure 12.10, in which each agent uses its directed path from S, is a Nash equilibria, and moreover it is the unique Nash equilibria for this instance. Proof: to verify that the given solution is a Nash equilibria, we simply need to check that no agent has an incentive to switch from its current path. But this is clear since all agents are paying at most 1, and the only other option, the currently vacant outer path, has cost 1 plus epsilon. Now suppose there were some other Nash equilibrium. In order to be different from the solution we have just been considering, it would have to involve at least one of the agents using the outer path. Let Tj1, Tj2, and so on until Tjl be the agents using the outer path, where J1 is less than J2, is less than J3, and so on, which is less than Jl. Then all these agents are paying 1 plus epsilon divided by L. But notice that Jl is greater than or equals to L, and so agent Tjl has the option to pay only 1 divided by Jl, which is less than or equals to 1 divided by L, by using its alternate path directly from S. Hence, Tjl has an incentive to deviate from the current solution, and hence this solution cannot be a Nash equilibrium. Figure 12.8b already illustrated that there can exist a Nash equilibrium whose total cost is much worse than that of the social optimum, but the examples in figure 12.9 and 12.10 drive home a further point. The total cost to all agents under even the most favorable Nash equilibrium solution can be worse than the total cost under the social optimum. How much worse? The total cost of the social optimum in this example is 1 plus epsilon, while the cost of the unique Nash equilibrium is 1 plus 1 divided by 2 plus 1 divided by 3 and so on plus 1 divided by k, which is equals to the summations of 1 divided by I, summing for all index I starting from 1 to k. We encountered this expression in chapter 11, where we defined it to be the harmonic number h of k and showed that its asymptotic value is h of k equals to theta of log k. These examples suggest that one can't really view the social optimum as the analog of the global minima in a traditional local search procedure. In standard local search, the global minima is always a stable solution since no improvement is possible. Here, the social optima can be an unstable solution, since it just requires one agent to have an interest in deviating. 2 basic questions. Best response dynamics can exhibit a variety of different behaviors, and we've just seen a range of examples that illustrate different phenomena. It's useful at this point to step back, assess our current understanding, and ask some basic questions. We group these questions around the following 2 issues. The existence of a Nash equilibrium. At this point, we actually don't have a proof that there even exists a Nash equilibrium solution in every instance of our multicast routing problem. The most natural candidate for a progress measure, the total cost to all agents, does not necessarily decrease when a single agent updates its path. Given this, it's not immediately clear how to argue that the best response dynamics must terminate. Why couldn't we get into a cycle where agent T1 improves its solution at the expense of T2, then T2 improved its solution at the expense of T1, and we continue this way forever? Indeed, it's not hard to define other problems in which exactly this can happen, and in which Nash equilibria don't exist. So if we wanted to argue that best response dynamics leads to a Nash equilibria in the present case, we need to figure out what's special about our routing problem that causes this to happen. The price of stability. So far, we've mainly considered Nash equilibria, in the role of observers. Essentially, we turn the agents loose on the graph from an arbitrary starting point and watch what they do. But if we were viewing this as particle designers trying to define a procedure by which agents could construct the paths from S, we might want to pursue the following approach. Given a set of agents located at nodes T1, T2, T3 until Tk, we could propose a collection of paths, one for each agent, with two properties. One, the set of paths forms a Nash equilibrium solution, and two, subject to one, the total cost to all agents is as small as possible. Of course, ideally, we'd like just to have the smallest total cost, as this is the social optimum. But if we propose the social optimum and it's not a Nash equilibrium, then it won't be stable. Agents will begin deviating and constructing new paths. Thus, properties 1 and 2 together represent our particles' attempt to optimize in the face of stability, finding the best solution from which no agent will want to deviate. We therefore defined the price of stability for a given instance of the problem to be the ratio of the cost of the best Nash equilibrium solution to the cost of the social optima. This quantity reflects the blow-up in cost that we incur due to the requirement that our solution must be stable in the face of the agent's self-interest. Note that this pair of questions can be asked for essentially any problem in which self-interested agents produce a collective solution. For our multi-case routing problem, we now resolve both these questions. Essentially, we will find that the example in Figure 12.10 captures some of the crucial aspects of the problem in general. We will show that for any instance, best response dynamics starting from the social optimal leads to a Nash equilibrium whose cost is greater by at most a factor of h of k, which is equals to theta of log k. Finding a good Nash equilibrium. We focus first on showing that best response dynamics in our problem always terminates with a Nash equilibrium. It will turn out that our approach to this question also provides the necessary technique for bounding the price of stability. The key idea is that we don't need to use the total cost to all agents as the progress measure against which to bound the number of steps of best response dynamics. Rather, any quantity that strictly decreases on the path update by any agent and which can only decrease a finite number of times will work perfectly well. With this in mind, we tried to formulate a measure that has this property. The measure will not necessarily have as strong an intuitive meaning as the total cost, but this is fine as long as it does what we need. We first consider in more detail why just using the total agent cost doesn't work. Suppose to take a simple example that agent Tj is currently sharing with X other agent a path consisting of the single HE. In general, of course, the agent's paths will be longer than this, but single H paths are useful to think about for this example. Now suppose that Tj decides it is, in fact, cheaper to switch to a path consisting of a single HF, which no agent is currently using. In order for this to be the case, it must that Cf is less than Ce divided by x plus 1. Now, as a result of this switch, the total cost to all agents goes up by Cf. Previously, x plus 1 agents contributed to the cost Ce, and no one was incurring the cost Cf. But after the switch, X agents still collectively have to pay the full cost Ce, and Tj is now paying an additional Cf. In order to view this as progress, we need to redefine what progress means. In particular, it would be useful to have a measure that could offset the added cost Cf via some notion that the overall potential energy in the system has dropped by CE divided by x plus 1. This would allow us to view the move by Tj as causing a net decrease since we have Cf less than Ce divided by x plus 1. In order to do this, we could maintain a potential on each He with the property that this potential drops by Ce divided by x plus 1 when the number of agents using E decreases from x plus 1 to x. Correspondingly, it will need to increase by this much when the number of agents using E increased from x to x plus 1. Thus, our intuition suggests that we should define the potential so that if there are x agents on an He, then the potential should decrease by Ce divided by x when the first one stops using E, by Ce divided by x minus 1 when the next one stops using E, by Ce divided by x minus 2 for the next one, and so forth, setting the potential to be Ce times 1 divided by x plus 1 divided by x minus 1 plus 1 divided by x minus 2 and so on plus 1 divided by 2 plus 1 is equals to C times h of x, where h is the harmonic function, is a simple way to accomplish this. More concretely, we define the potential of a set of paths P1, P2, P3 until Pk, denoted as phi of P1, P2, P3 until Pk as follows. For each He, let Xe denote the number of agents whose paths using the He. Then phi of P1, P2, P3 until Pk is equals to the summations of Ce times h of Xe, summing for all little h little e, which is in capital E. We will define the harmonic number h of 0 to be 0, so that the contribution of agencies containing no paths is 0. The following claim establishes that phi really works as a progress measure. 12.14. Suppose that the current set of paths is P1, P2, P3 until Pk, and agent Tj updates its path from Pj to Pj prime. Then the new potential phi of P1, P2, P3 until Pj minus 1, Pj prime, Pj plus 1, Pj plus 2, and so on until Pk is strictly less than the old potential phi of P1, P2, P3 until Pj minus 1, Pj, Pj plus 1, and so on until Pk. Proof: before Tj switched its paths from Pj to Pj prime, it was paying the summations of Ce divided by Xe, summing for all E in Pj. Since it was sharing the cost of each He with Xe minus 1 other agents. After the switch, it continues to pay this cost on the agencies in their intersection, Pj intersected Pj prime, and it also pays Cf divided by Xf plus 1 on each Hf in Pj prime minus Pj. Thus, the fact that Tj viewed this switch as an improvement means that the summations of Cf divided by Xf plus 1, summing for all f in Pj prime minus Pj, is less than the summations of Ce divided by Xe, summing for all E in Pj minus Pj prime. Now let's ask what happens to this potential function phi. The only agencies on which it changes are those in Pj prime minus Pj and those in Pj minus Pj prime. On the formal set, it increases by the summations of Cf times the harmonic function h of xf plus 1 minus h of xf, summing for all f which is in Pj prime minus Pj, which is equals to the summations of Cf divided by xf plus 1, summing for all f in Pj prime minus Pj. And on the later set, it decreases by the summations of Ce of h of xe minus h of xe minus 1, summing for all E in Pj minus Pj prime, which is equals to the summations of Ce divided by xe, summing for all E in Pj minus Pj prime. So the criterion that Tj used for switching paths is precisely the statement that the total increase is strictly less than the total decrease, and hence the potential phi decreases as a result of Tj's switch. Now there are only finitely many ways to choose a path for each agent Tj, and 12.14 says that best response dynamics can never revisit a set of paths P1, P2, P3 until Pk once it leaves it due to an improving move by some agent. Thus, we have shown the following. 12.15 Best response dynamics always leads to a set of paths that forms a Nash equilibrium solution. Bounding the price of stability, our potential function phi also turns out to be very useful in providing a bound on the price of stability. The point is that although phi is not equal to the total cost incurred by all agents, it tracks it reasonably closely. To see this, let C of P1, P2, P3 until Pk denote the total cost to all agents when the selected paths are P1, P2, P3 until Pk. This quantity is simply the sum of Ce over all ages that appear in the union of these paths, since the cost of each such age is completely covered by the agents whose paths contain it. Now the relationship between the cost function C and the potential function phi is as follows. 12.16 For any set of paths P1, P2, P3 until Pk, we have C of P1, P2, P3 until Pk, which is less than equals to phi of P1, P2, P3 until Pk, which is less than equals to h of k, where h is the harmonic function, times C of P1, P2, P3 until Pk. Proof. Recall our notation in which xe denotes the number of paths containing he. For the purposes of comparing C and phi, we also define E plus to be the set of all h's that belong to at least one of the paths P1, P2, P3 until Pk. Then, by the definition of C, we have C of P1, P2, P3 until Pk, which is equals to the summations of Ce summing for all little e in capital E plus. A simple fact to notice is that xe is less than equals to k for all e. Now, we simply write C of P1, P2, P3 until Pk, which is equals to the summations of Ce summing for all little e in capital E plus, which is less than equals to the summations of Ce times h of xe summing for all little e in E plus, which is equals to phi of P1, P2, P3 until Pk, and phi of P1, P2, P3 until Pk is equals to the summations of Ce times h of xe summing for all little e in capital E plus, which is less than equals to the summations of Ce times h of k summing for all little e in capital E plus, which is equals to h of k times C of P1, P2, P3 until Pk. Using this, we can give a bound on the price of stability. That is 12.17. In every instance, there is a Nash equilibrium solution for which the total cost to all agents exists that of the social optima by at most a factor of h of k. Proof. To produce the desired Nash equilibrium, we start from a social optimum consisting of paths P1 star, P2 star, P3 star, and so on to Pk star, and run a best response dynamics. By 12.15, this must terminate at a Nash equilibrium P1, P2, P3 until Pk. During this run of best response dynamics, the total cost to all agents may have been going up, but by 12.14, the potential function was decreasing. Thus, we have phi of P1, P2, P3 until Pk, which is less than equals to phi of P1 star, P2 star, and so on to Pk star. This is basically all we need, since for any set of paths, the quantities C and phi differ by at most a factor of h of k. Specifically, C of P1 P2 P3 until Pk is less than equals to phi of P1 P2 P3 until Pk is less than equals to phi of P1 star, P2 star, and so on until Pk star, which is less than equals to h of k times C of P1 star, P2 star, and so on until Pk star. Thus, we have shown that a Nash equilibrium always exists, and there is always a Nash equilibrium whose total cost is within an h of k factor of the social optima. The example in figure 12.10 shows that it isn't possible to improve on the bound of h of k in the worst case. Although this wraps up certain aspects of the problem very neatly, there are a number of questions here for which the answer isn't known. One particularly intriguing question is whether it's possible to construct a Nash equilibrium for this problem in polynomial time. Note that our proof of the existence of a Nash equilibrium argued simply that as best response dynamics iterated through sets of paths, it could never revisit the same set twice, and hence it could not run forever. But there are exponentially many possible sets of paths, and so this does not give a polynomial time algorithm. Beyond the question of finding any Nash equilibrium efficiently, there is also the open question of efficiently finding a Nash equilibrium that achieves a bound of h of k relative to the social optima, as guaranteed by 12.17. It's also important to reiterate something that we mentioned earlier. It's not hard to find problems for which best response dynamics may cycle forever, and for which Nash equilibria do not necessarily exist. We were fortunate to hear that best response dynamics could be viewed as iteratively improving a potential function that guaranteed our progress toward Nash equilibria. But the point is that the potential functions like this do not exist for all problems in which agents interact. Finally, it's interesting to compare what we've been doing here to a problem that we considered earlier in this chapter, finding a stable configuration in a Hopfield network. If you recall the discussion of that earlier problem, we analyzed a process in which each node flips between two possible states, seeking to increase the total weight of good agencies incident to it. This can in fact be viewed as an instance of best response dynamics for a problem in which each node has an objective function that seeks to maximize this measure of good edge weight. However, showing the convergence of best response dynamics for the Hopfield network problem was much easier than the challenge we faced here. There it turned out that the state flipping process was in fact a disguised form of local search with an objective function obtained simply by adding together the objective functions of all nodes. In fact, the analog of the total cost to all agents served as a progress measure. In the present case, it was precisely because this total cost function did not work as a progress measure that we were forced to embark on the more complex analysis described here.